last few sections that we got going on here, talking about the carbon-13 NMR. This is helpful still. I know there's a lot into proton NMR that we use, and it's really, really helpful to determine structure. And I know at this point, probably a bunch of you are like, well, I just like the proton NMR. Let's just stop here. Carbon-13 NMR is still really, really helpful. We talked about this before with having an odd number in the nucleus, right? Proton 1, that idea is usually because that is the most abundant isotope of hydrogen, and we tend to have a lot of hydrogens in our organic compounds. These signals are really easy to obtain. They're really strong. Carbon-13 only accounts for 1% of the carbons in nature, 1.1%. So you really need a sensitive NMR and a really concentrated sample to do a proton or to do a carbon-13 NMR. For proton NMR, we talked about where the chemical shift was, the splitting patterns, integration, all of those are important. The only thing that's important in carbon-13 NMR is the number of signals and the chemical shift. So there's two characteristics, signals and shift, that we will be considering. In the carbon-13 NMR, we do have splitting with protons and carbon-13, and it's often so complex that we can't read it. So what we have is a decoupled carbon-13 NMR signal. What we do is we try to decouple the number of signals so that it's easier to determine the carbon-13 spectra. And so what we'll see is that all of our carbon-13 spectra will be singlets. All right, so we won't see any doublets or triplets or anything like that, because what happens in carbon-13 NMRs, if we don't decouple, is that the protons actually get involved, and that's just not fun. So we can compare proton NMR to carbon-13 NMR in the same idea as different frequencies of energy to excite and resonate nuclei. We will see a TMS standard, but carbon-13 NMR generally appears between 0 ppm and 220 ppm. So there's a bigger range here because of the carbon nuclei having 13 species, 13 protons and neutrons in the nuclei rather than hydrogen's just one. So carbon-13 NMR is a unique type of signal. And so each carbon-13 NMR spectrum represents a unique type of carbon. Planes and axes of symmetry can cause carbon atoms to be electronically equivalent. So let's take a look at a couple of molecules and we'll start to see how symmetry affects, right? Just the same as proton NMR. Just the same as proton NMR, we see how symmetry can affect our molecules. So this is our same idea as what we were talking about at the end of the proton NMR. 3 different types of benzene with 2 methyl groups being distributed across. When we see a plane of symmetry, boop, 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 right down there, this side, I'll label this A, is the same as that side. B, same as that side. C, and D, right? Same plane of symmetry, just locating a couple different places. We have 1 carbon here. We have 2 carbons over here that are the same. These are the same. These are the same. That's different, right? And when we have perfect symmetry, whoo, we have a lot of things that are the same. The methyl groups, B, B, and then all 4 of these leftover carbons are the same. So when we're thinking about structure, what's really important is to be able to find symmetry or lack thereof, right? Symmetry right here. So we can expect A, B, and C, 3 signals for something like pentane, right? Awesome. If we were to throw in something that's not symmetrical, now our molecule is not symmetrical anymore, all 5 of these carbons are different, right? Beautiful. So same way that we've dissected the molecules before in talking about symmetry and looking at equivalent carbons, now it's a little bit easier, I think, in carbon-13 NMR than in proton NMR because you don't have C2 groups, right? You have just plain old carbons, and we're not focusing on multiply attached hydrogens. Like the proton signals, chemical shifts for carbon-13 NMR are affected by shielding or de-shielding. Again, the same way, sp3 hybridized carbons are usually down here at the 50 to 0 ppm range. And then sp hybridized and sp3 hybridized with de-shielded, some electronegative atoms appear in the middle. So our triple bonds and carbons to nitrogens, carbons to oxygens. sp2 hybridized carbon atoms are in between 100 and 150 ppm. And then our carbonyl compounds are between 150 and 220. So let's just start recording some stuff here. This is what a typical spectrum will look like. This is an ester compound that I'm looking at here, and there are 5 carbons up at the top in that structure. What we want to do here is just be able to match to start off the bat. We'll get into harder questions when we meet, but matching the carbons here, they are labeled. So I just want to make sure we know which ones are which. Again, CdCl3 is a type of solvent. It's a deuterated chloroform so that there are no protons in it, so that it is just a solvent for us, all right? Now, the C2, what's labeled as C2 way down here, is most likely our carbonyl. Why? Because it is an sp2 hybridized carbon and it appears greater than 150. Remember, between 150 and 220 are our carbonyl compounds. So that's C2. Coming up here, this range, if we want to look at which carbon is C3 up here. Remember, shielding and de-shielding, just like in proton NMR. We don't have to do any math here, but we do know the further downfield, the further to the left, the closer you are to an electronegative atom. So the carbon, the CH2 group, attached to the oxygen of the ester is closest to the most electronegative atom, oxygen. And so that is why we're going to label that CH2 group as number 3. So I'm just going to label closer to oxygen of ester for our reason why. All right, let's look at C1 here, the next carbon in our chain. Which one of our leftover outer terminal carbons is C1? Most likely it's going to be this one because it's alpha to the carbonyl. Right? And then our final carbon 4 here, beta to oxygen. So again, doesn't get shifted downfield as much, and it is the furthest away from any sort of electronegative source. So this is how we can whittle through a carbon-13 spectrum. Now, the distortionless enhancement by polarization transfer, or DEPT, carbon-13 NMR spectroscopy is extremely helpful because carbon-13 doesn't give only gives singlets, and it doesn't provide information about numbers of hydrogens attached to each atom or neighbors or anything like that. Carbon-13 by itself is actually pretty difficult to start to analyze. We like using DEPT carbon-13 NMRs because they can actually provide more information to the number of hydrogen atoms attached to each carbon. Like this, DEPT 90 only shows CH signals. What? That's pretty cool. DEPT 135 will show the CH3 and CH and give them a positive signal that shoots upward, just like our typical signals. I'll show you what that looks like in a second. The CH2, it will actually shoot that into the negative in the downward position. So now what DEPT 90 and 135 can do is actually elucidate the type of carbons we have, CH, CH2, or CH3, and be able to look at the signals that stay or the signals that disappear as being able to elucidate that information. Let's go ahead and just look at this chart. This chart is very, very helpful. Broadband decoupled is when everything shows up and everything's a singlet spike. That's what we just did, right? Dep 90 only shows a CH group. Nice. So you can take a broadband decoupled and a Dep 90 and compare them and say, oh, any peak that shows up on my Dep 90 and was on my broadband decoupled carbon NMR, that must be a CH group. Any group that disappeared is not a CH group. If it doesn't show up on Dep 90, it's not a CH group. And then a Dep 135 will be able to elucidate that CH2 group. It also important, remember we've talked about this since IR, not showing signals is just as important as showing the signals. So look to where there's absences on these, right? A Dep 135 will invert the CH2 group signal and make it go downward, and it will eliminate our carbon groups with just tetrasubstituted carbons. So this could be carbonyl groups. This could be the carbon that's holding 3 methyls in a butyl group, things like that. So we want to compare, right? We wouldn't ever do a Dep 135 without doing a broadband decoupled, or a Dep 90 without doing a broadband decoupled carbon NMR spectrum. So we have diethyl phthalate up here. I chose this one just because it was of the symmetry, honestly, and it's real life application with the phthalates. Diethyl phthalate here, let's just identify a couple of signals, right? A, B, C, D, E, F on the top is the same as that on the bottom. And so we should see 6 peaks. But what's really, really important here is the idea of a couple of these that we see. The aromatic CHs are kind of shoved in here, and the aromatic C for carbon D is a little hard to see as well. But we'll try to elucidate these 6 peaks as much as possible, okay? And so we do see 1, 2, 3, 4, 5, 6 peaks. I'm not going to label them A, B, and C yet because I want to make sure that we see that there are 6 peaks. We understand what those 6 peaks could represent, and now we're going to try to elucidate with the decoupled carbon NMR, the Dep 90, and the Dep 135, what each one of these is. So again, looking and referring to our table that we just saw way up here, table 15.4, what we want to be able to do is identify which groups are carbons, which ones are CHs, which ones are CH2s, and which ones are CH3s. So without looking at the structure right now, let's just start to identify what we see in comparison from the decoupled carbon 13 NMR to the Dep 90. Remember, Dep 90 only shows CH groups. This signal and this signal still appear. I'm going to highlight them. This one and this one, these two. The signal 3 and 4 still appear. So these must be CHs. They also appear in the range around 120, 130. So they must be aromatic CHs, right? Those sp2 carbons with 1 hydrogen, all right? Now, let's move up to the Dep 135. There is still our 2 CH groups, right? We see this negative peak for this one right here. So this must be a CH2 group, right? Because the CH2 group in a Dep 135 is inverted. Beautiful. And then the last peak that I want to see here was absent in the Dep 90, but present in the Dep 135. That means it must be a CH3 group, all right? Awesome. Things that are absent in both the Dep 135 and the Dep 90 are going to be our plain old carbons. carbons without hydrogens. We have a few of them. This guy up at 165, and this one, which was around 135. Now, we have two carbons in that structure, D and C, that are those C groups without hydrogens. We're going to label this as carbon C and this one as D. Why? Because we know the carbonyl would be, the carbonyl carbon is going to be more de-shielded because it's double bonded to an oxygen, and so it should be further downfield, right? Just like we expected. The two aromatic groups, E and F, E is probably the one that's closest to the carbonyl. F is probably the one that is furthest upfield, further away from the carbonyl, right? So we would probably label E as the signal number 4 there, and F as signal number 3. CH2 group, B, the carbon adjacent to the oxygen of the ester. And then finally, A, the CH3 group. Excellent. So this identification of CH, CH2, and CH3 groups with the depth 135 and the depth 90 with the CH groups is extremely helpful to start to elucidate the positions of each of these carbon peaks. Also, don't forget those peaks highlighted in green. What is absent from both the depth 135 and the depth 90 are our carbonyl groups and our fully substituted carbons, the carbons with no hydrogens. Where can we see NMR before? In real life, if you've ever seen or had an MRI done, magnetic resonance imaging, it is essentially a proton NMR, just taken on a human body, right? The body is analyzed rather than a sample in an NMR tube, but we are made up of a bunch of different nuclei, and different tissues actually have different concentrations of protons. So the MRI gives a 3D image of different types of tissue. Radio waves and magnetic fields are very, very mild, so that we have no side effects. But again, you're sitting in a pretty big NMR when you think about getting an MRI in the medical field. So this is a truly medically applied type of instrumentation, which is just really awesome that we can do this with the human body.